please welcome Professor Wendy Freedman.
I am standing outside of a cabin, a young girl of 7, with my father. We are looking up at a dark sky with more stars than I've ever seen before. And my father is explaining to me that the stars are at unimaginable distances from us, and that some of them might not even be there anymore. We're looking at them as they were when their light began its journey to us, and some of them may have died in the meantime. The journey might be many thousands and thousands or more years ago. I was completely blown away, and my mind was racing with questions. How could we tell how far away the stars are, or how old they are, and how big is the universe? I didn't know it then, but that was the moment that would drive my entire scientific career. For thousands of years, our ancestors have gazed up at the night sky, eventually charting and then using the positions of stars and planets. And today, we continue to look up and to explore. We are bound to that human curiosity. My scientific journey has taken me to distant mountaintops in Hawaii, in the Andes Mountains in Chile, and I spend much of my time studying incredible images from the Hubble Space Telescope and the James Webb Space Telescope. I study stars with peculiar names like Cepheids, red giants, supernovae, all stars with unique properties that allow us to measure how far away they are. I chart the rate at which the universe is expanding, a quantity that is called the Hubble constant. The Hubble constant is more than just a rate. It tells us how big the universe is and how old it is. My job description is literally measuring the size and age of the universe. The Hubble constant gives us the bedrock for our understanding of the universe. It's like setting the scale on a map. If the scale is off, then all our distances and times are off too. Ultimately, the Hubble constant also represents something even bigger. It's humanity's attempt to understand our place in the cosmos. It connects us to the origin of everything, to the future fate of the universe, and to the deep laws of physics that govern space and time. In short, it's not just a number. It's a key to the story of the universe itself. But it's a quantity that's proved notoriously difficult to measure. Astronomers have been in this pursuit for almost a century, and we're still on this trail today. So how do we measure the Hubble constant? Well, before I jump ahead to one of the most exciting moments in my career, a moment that would help us answer one of the most vexing and outstanding problems in astronomy, let me take you on a rapid ride through 100 years of astronomical discovery. Ready? Buckle up, because we're going to cover billions of light years in just a few minutes. Imagine that dark sky again. How can we tell how far away the stars are? We see bright stars and we see faint stars. Do they all have the same wattage? Like light bulbs, when we look more distant, the farther away they are, the fainter they look. Or are they all at the same distance but have a range in brightness? Or both? A first breakthrough came in 1908 with a discovery by the astronomer Henrietta Leavitt, who was working at the Harvard College Observatory. And Leavitt was studying a kind of a star called a Cepheid. These are stars that change their brightness with a steady rhythm, like cosmic beacons. And what Henrietta found was that the brighter the Cepheid, the slower it changed its brightness, maybe over periods of weeks. And the fainter stars varied more quickly over periods of days. By timing the rate at which a Cepheid varies, we tell its true brightness. Then we can measure how faint it appears from the Earth and calculate its distance. And in nearby galaxies, we can measure dozens, if not hundreds, of these stars. Leavitt's discovery gave us a reliable way then to map the scale of the universe. A second breakthrough came in the 1920s with astronomer Edwin Hubble of the Carnegie Observatories, where I used to be the director. And Hubble used Leavitt's cosmic beacons to make two incredible discoveries. First, he found that our Milky Way galaxy is but one of hundreds of billions of galaxies in the universe that's visible to us. And next, and even more astonishing, he found that the farther away a galaxy is, the faster it's moving away from us. The universe is expanding. And if it's expanding today, then like playing a movie in reverse, we can tell how long it's been expanding. But despite decades of intense effort after Leavitt and Hubble's discoveries, astronomers had locked into a fierce debate about whether the Hubble constant was 50 or 100, which led to a range in age for the universe of 20 billion to 10 billion years. Now, getting the age wrong by 10 billion years is a pretty big deal. With astronomer Barry Madore, we set out to close this gap. And interestingly, many of the same questions that had intrigued me when I was young now confronted me as I became a professional astronomer. So we devised a method to correct for the effects of astronomical dust, dust that had largely been swept under the rug, the cosmic rug, so to speak. So why is this dust a problem? Here's a photo of the sun during a raging fire. The sun's pretty high up in the sky, but it looks red and fainter. Why? Because the ash from the fire is scattering and absorbing its light. And we astronomers face a similar problem when we look out into space. Tiny cosmic dust grains scatter and absorb the light that's coming from distant stars. And in some cases, the dust is so thick we can't see any stars through it. And if we can't measure the true brightnesses, then our entire map of the universe is off. A third breakthrough came in the 1980s with a kind of cosmic dust-correcting glasses for telescopes. For over a century, astronomers had used photographic cameras, which record only a tiny fraction of the light that's coming from distant stars. But just as I began my career, telescopes got a huge, spectacular upgrade. Digital detectors called CCDs. CCDs are like powerful versions of the sensors in our smartphones, and they can collect almost all of the incoming starlight. And then new infrared instruments allow us to peer even further past the dust into the distant stars, and suddenly we could measure distances across vast regions in the universe. These three breakthroughs, Leavitt's cosmic beacons, Hubble's discovery of the expansion, and CCDs that allowed us to sweep away the cosmic dust, all came together in the 1990s, enabling one of the most challenging problems in astronomy to be addressed, that of measuring an accurate value of the Hubble constant. And it's a project that came to be called the Hubble Space Telescope Key Project. And I had the immense privilege of leading the international team that carried out the science program. Over 300 miles in orbit about the Earth, at a speed of 17,000 miles per hour, the Hubble Space Telescope promised 10 times the image clarity of previous telescopes on the Earth. In using CCDs and the same kinds of Cepheids used by Leavitt and Hubble, our team measured a value for the Hubble constant of 72, finally settling this long-standing debate between 50 and 100, and calculating an age for the universe of 13.7 billion years, opening the way for future cosmic discovery. So after decades of effort, we did it. In the following decade, while I was the director of the Carnegie Observatories, I switched gears and I became the founding leader of an exciting international project to build a giant telescope with a mere 80 feet in diameter to be located in the Andes Mountains in Chile. So this mirror would take up the entire theater, and the telescope will stand as high as the Statue of Liberty. It's one of the most ambitious scientific projects of the 21st century. It will be powerful enough that we could detect a candle on the moon, if you could actually burn a candle on the moon. And it may have the potential to be the first telescope to discover life elsewhere beyond our own solar system. It's poised for completion in the mid-2030s. It's a telescope for the next generation. But then I got a call from the president of the University of Chicago urging me to come back to full-time research. And I couldn't resist, because measurements of the Hubble constant were starting to show that something was amiss in our understanding of the cosmos. A relatively new way of measuring the Hubble constant using the faint afterglow radiation from the Big Bang gives a value of the Hubble constant of 67, lower than the recent value from Cepheids of about 73. Now, whether this now smaller difference is of comic or cosmic significance, that's the million light-year question. Astronomers have given a name to this mismatch, the Hubble tension, which makes it sound either like a giant cosmic headache or maybe an anxious holiday dinner with rival cosmologists. I don't know any of those. It's almost as if Michelangelo, who was painting the Sistine Chapel, maybe he did it from different sides of the ceiling, missed the connection. Or put it another way, either we have undetected errors in our measurements, or something is missing from our understanding of the universe. Maybe there's something missing from what we call our standard cosmological model. Well, what is the standard model? Everything that we can see, stars, galaxies, planets, butterflies, car keys, makes up only about 5% of the universe. And two new ingredients, dark matter at a level 5 times that of ordinary matter, and dark energy, which is causing the universe to accelerate, together they make up a staggering 95% of the universe. So the Hubble tension is like finding a small crack in what we thought was a solid foundation. Maybe it's nothing, or maybe it's a clue to something even bigger, some piece of missing physics beyond the standard model. But given the challenge in measuring an accurate value of the Hubble constant, we better improve the accuracy so that we can nail down where this tension is arising. On Christmas Day 2021, an incredible telescope was launched into space, embarking on a journey 1 million miles away from the Earth. The James Webb Space Telescope has a collecting area of 7 times that of Hubble and 4 times its image clarity. It was designed with infrared capability, so it's less sensitive to the cosmic dust, which makes it ideal for measuring cosmic distances. Only about 1 in 10 proposals gets granted time on the telescope. I now lead a group at the University of Chicago with the goal of improving the accuracy in the Hubble constant. And we're using, again, Cepheids. This is an image of a Cepheid 60 million light years away from the Earth. It's an image taken with Hubble. It looks kind of fuzzy. But you can see immediately the jump in the image clarity and the accuracy with which we can measure the brightness of these Cepheids and therefore their distances. So we're using Cepheids. We've developed methods to use stars called red giants, and we've developed a new method, stars rich in carbon, which are good distance markers. And then we step out into the universe using supernovae, very bright explosions of stars. And our team has found a value of the Hubble constant based on our Webb observations of 70. And given the margin of error, it aligns pretty well with the value from the standard model. But even with this level of precision, scientists are genuinely excited by the possibility that we could be seeing something important. Some hint of new physics beyond the standard model, some unknown influence at work in the universe. I love this image. It's an actual image of the sky. And it's almost as if the universe is trying to tell us we don't yet have all the answers to the questions we're asking. In school, we're often taught that science is about finding the right answer, the one printed in the back of the book. But in Science at the Forefront, there is no back of the book. We're venturing into uncharted territory, and that's the exciting thing. New discoveries, new precision measurements don't close the book. They turn the page. They open up new possibilities, new ways of seeing the universe. And that's part of the beauty of it. The more we learn, the more we realize how much left there is to explore. I remember a night at a remote observatory observing with a student during a meteor shower. And every few moments I'd look up and see a beautiful bright streak across the dark sky. But my student kept missing them. And finally she turned to me in frustration and said, "I just don't see anything." And so I paused and then said with some humor, "Well, you have to look up." When we look up at the sky, we're tapping into something ancient and universal. Science isn't just about standing on the shoulders of giants. It's a collective human endeavor, a continuation of a conversation that's been going on for thousands of years. Since the earliest civilizations carefully mapping the skies to today's telescopes peering billions of light years into space, each generation builds on the last. We pass on knowledge, we make new discoveries, we refine our ideas, and we let go of the ones that no longer hold up. We've made a lot of progress on answering some of the questions that drove my early career, but now even more mysteries have surfaced. The immense dark frontier remains for us to understand. I like to imagine that future generations will use the Giant Magellan Telescope to solve some of these mysteries. And I can see some young people in the audience tonight. Maybe one of you will walk out of the theater tonight, look up at the Chicago sky, and ask a question that will lead to a next great discovery. Maybe that will be you. Thank you very much. Thank you.